Hey, this is Bill Mather, the TA for 255, and I'm just going to go over problem 3 on homework 3. I'm just going to do the entire thing and just give you guys a good idea on how to do it. So what the system asks for is for the electromechanical system below, derive the transfer function G, which is the relationship between this output position of the mass and the input voltage. So we already have a transfer function between the motor and its output shaft that was given in the notes. So what we need to do is we need to follow the method provided in the lecture notes and find the output inertia and drag, inertia and damping that this contributes to the motor model, and then inject that into the motor model and then use the motor model to solve for the output position. So our steps are we need to find the inertia and damping that this output load provides to the motor. We need to add that back into the motor model, and then we'll have a relationship between the motor model and the output shaft, and then we need to relate the output shaft to the motor back to the position of this mass. So let's go ahead and do that. So for the system, we have the input going through N1 and N2, this gearing that goes into the gear, which is on the rack, and the gear has a damping coefficient, and this mass also has damping as well. So let's go through the process of how to solve that. So what we need to do is we need to find the load that this mechanism is presenting to the motor. So to do that, what we can do is we can put a test torque onto this system. So actually, let me just draw the system myself. Okay, so I have the motor. That's the motor. It's going to go into the gearing. That's going to be attached to the mass. That goes into a dampener. And this goes into a dampener. Okay. This is just J and D, F, V, M. And this has a radius of 2. Okay. So what we can do with the system is we can, like I said, we can inject a test torque at this location. And we'll call that torque X. And we can solve for what the equations of motion would be after torque X. And the advantage of doing that is that's just separating the system out into two problems. We're just looking at the load that this presents. Then we'll convert that load to the load it presents before the gearing. And then once we have that, we'll have the J term and the D term that we can then add to the motor model. So if I just look at the input torque X, and let me define all the directions that I care about. If I draw the, he's already defined X for us. I'm going to define this theta as going this direction. And I'm going to find torque X also going in that direction. Okay. And by that direction, I mean like this, towards us on top. And yeah, now I'm just going to solve for the equations of motion of this inertia. So for the J inertia, the equations of motion are going to be the input torque X plus there's torque from the rack that's sitting there. So I'm going to call that torque mass. That's the torque on the body that's provided from this other system. Okay, that's going to equal the factors that resist the input torques, which is the inertial term, which is going to be J S squared theta, and also the damping term, plus ds theta. So now we also want to solve the same set of equations for m, but we need to actually know the direction that the force is going for m, because since we've defined torque mass as going like this on that inertial body, we need to make sure that the force m is defined in the same direction. So I'm going to draw a blow up of the gear. So this is the gear, and this is the rack. Okay, we've defined the direction of theta to be this. We've also defined the torque direction. The test torque the mass torque, we're defined that direction as well. If it's going that direction, it's going to put a upward force on this side. But if it's putting an upward force on this side, that means the rack has to have the equal and opposite counterforce, because it's in sort of the initial idea, it's not going to be moving. So that means it's Fm. If we had an F mass that we're going to add to this equation, it's going to be pointed down. And x is also pointed down. Okay. So if we want to relate, we want equations to relate theta to x and relate T mass to F mass. What we have is that the T mass from the previous equation, equation 1, is equal to R F mass. And we have that x is equal to negative r theta. Okay. We see that as theta increases, it'll actually pull the rack up, which means x was coming up. Okay. So now we can do the equations of motion for the mass. The equation of motion for the mass is going to just be F mass is equal to ms squared x plus fvs x. Okay. So now what we can do is we can combine equations 1 and 2 and also use these equations for how to relate theta to x and F mass to torque mass to simplify this equation, so we just have torque x and theta. So we're just going to plug this F mass, this R F mass in for T mass. So if we do that, again, we're going to sub 2 into 1, and that's going to give us torque x minus R F mass, which is going to be R, we'll just say plus R times ms squared times negative r theta plus R fvs times negative r theta is equal to js squared theta plus ds theta. Now we move everything to the right-hand side, so we just have torque x on the left-hand side. Torque x is equal to js squared plus r squared ms squared plus ds plus r squared fvs as an entire quantity multiplied by theta. So all I did was I resorted the terms out. So here are the two s squared terms and here are the two s terms. Okay, so that gives me a relationship between this test torque I'm injecting and the actual output position of this shaft. Okay. That's good because what it's doing is it's showing me what the inertial load is. The inertial load is going to be this J plus R squared M. Everything gets multiplied by S squared. This is going to be sort of my J equivalent at this location. And this D plus R squared FV is going to be my D equivalent. Okay. Now these are after the gearing, so I need to step back through the gearing. So I'm going to do that in the next video. So we have this relationship, we have this J equivalent and D equivalent for an input test torque Tx, but what we really want is the equivalent J and D on the other side of the gearing. So let's do that now. Okay. So again, just for clarity, let's write J equivalent is equal to J plus R squared M, and D equivalent is equal to D plus R squared FV. Again, it's important this is actually after the gearing, so we need to convert those equivalencies to the equivalency before the gearing. So for that, we just use the transfer that was mentioned in notes, the n squared over n squared. So just for clarity, I'm going to actually write down how we actually get those numbers, because if you remember from recitation, I can never get it right, so I just wanted to be very clear about it. So the idea of J equivalency and D equivalency is those terms are actually a representation of, if I wanted to consider it, Tx over theta x. That's what the impedance is measured in, torque per change in position or change in radial position. So that's going to be this J plus R squared M S squared plus D plus R squared FV times S. Okay. And what we need to do is we need to take torque X, theta X, and represent it instead as torque M, the output torque of the motor, over theta M of the motor. So essentially we're putting another test torque in, or we're just reflecting this torque back to see what Tx is if it was actually at the motor, Tm. Okay. So we need to do this, so we can simply say that the relationship between the torques is just going to be torque X is equal to N, actually N, I never remember, N X over Nm. So that's on the X side and that's on the M side of torque M, which is equal to N2 over N1.